Is this? What's the crack? So what we're doing today is that we're going to look at simple harmonic motion and figure out how do we draw acceleration, velocity, and displacement time graphs for a mass on a spring. Okay, so the first thing I remember for simple harmonic motion is that the acceleration is always proportional to negative x. That's the first fact I write in. Then I'm going to look at my data sheet and I can see this fact here. So x equals a cosine wt. So I'm going to make a little note of what my graph looks like before I attempt the question. So I know for a sine graph, the way I remember a sine graph is, again, it's like a sin. So at time 0, it's like when you're a baby, you're born with 0 sins, and then over life, you gain sins. So then that's my sine graph. So then for a cosine graph, it's going to be the opposite. So this one starts at 0, cosine graph starts at positive, and you just finish your wave. Okay? So again, what I have is a spring, and it says it's pulled down a distance a. So I'm just going to sketch that. So here's my spring in its natural form, and what we're doing is we're pulling it down a distance a. So there is my equilibrium position, and I pulled it down a distance a, and that's when I'm starting my timer. Okay? So I have to think about what's the first thing that this mass is going to do, or what's the first thing the spring is going to do. So the first thing the spring is going to do is it's going to try to move upwards. Okay? And again, I know upwards is positive. So again, it's going to try to move upwards. So its velocity is going to be a positive number. Again, the acceleration is going to be towards the middle. And you think about it, it's starting way down here. So that its initial position is at negative a. So its x, its initial position is down here at negative a, and it's going to go up towards 0. So when I draw my graph, the first one, which is displacement time graph, what I said was the initial displacement is negative a. It starts at the bottom. So I'm going to mark on my negative a. That's where it starts. And we just said it's going to go up towards the 0 over time. Okay? So I look at my first equation from my data sheet was x equals a cosine wt. So that equation was written for a mass that instead of being pulled down first, negative a, for a mass that was compressed upwards by positive a. And then it was made to oscillate. So our equation is going to be slightly different because we've pulled it down, not pushed it up. So our equation for x is going to be negative a cosine wt. Okay, so again, I look at my shape of my cosine graphs. This is my cosine graph, but I want the negative version of it. So I reflect it in the x-axis. That makes sense because it started here. And then I just finish off my wave. Okay, so that's my displacement time graph. Okay, and we'll just mark on the key positions on our graph. Okay, so beneath it then, we're going to have a velocity time graph, and we're going to have to draw an acceleration time graph. Okay, and you probably want to keep these positions always the same because that's when the mass or the spring is changing how it moves. Okay, so I have my time stamps always the same in all frame graphs. Okay, I think the easiest one to start with is the acceleration time graph because for simple harmonic motion, acceleration is proportional to negative x. So if my displacement time graph started at negative a, my acceleration time graph is going to start at positive a. So I mark on my positive a. And again, I know it has to go under simple harmonic motion, which is the waveform. So what it's going to do, if I think about it, over here, it's going to start with positive a acceleration. That makes sense because it wants to get accelerated towards its equilibrium position, which is the upwards direction. So that's why it's positive a. Okay. Then what it's going to do is it's keep accelerating upwards in the positive direction, and then it comes back down again. Okay. So what I do is I sketch my graph, which is going to look like, oops, I just did that really bit again. I'm going to sketch my graph, which is going to look like this. So that's my acceleration time graph. Okay, so the last one then is my velocity time graph. So again, I want to look back at my picture and figure out what's happening. So when we start at negative a, when we start down here, the initial velocity wants to push it upwards towards 0. So again, if we think about our projectiles, when something is changing direction at maximum height, the speed was 0. So once it gets down here, it's trying to change direction. So it's actually starting with a speed of 0. Okay? It's trying to go upwards towards the 0. So as it goes upwards, its velocity is in the positive direction. It's going to be increasing. So my velocity has been in a positive direction and increasing. So then if I compare that to my graphs, I can clearly see that's a sine graph. So now I just finish off my graph. Okay? Just so we can do a bit of math, another way you could do that is differentiation. So if I have my x, I'm just going to write it over here to see the other way, is negative a cosine wt. What I can do is I can differentiate x with respect to time. And again, that could be your sense check. So if I differentiate x with respect to time, if we differentiate cosine, I get a negative sign. But if I differentiate negative cosine, I get a positive sign. And it's sine of wt. But when we differentiate a cosine, what happens is the w has to come outside and go to the front. So what I have now is a times w. So what I'm going to have is a times w. So what I should have drawn was a positive sine graph. So I checked, did I draw that? And I did. I drew a positive sine graph.